I modified my talk slightly from yesterday because of the following. I was only going to talk about the energy problem with this slide because the energy problem means different things to different people. It's an issue, it's a global energy and economic security and prosperity issue. There's a potential for geopolitical conflict because of the escalating competition, especially for oil and gas, and climate change. But I modified the talk because I met some people last night who were not so sure that climate change is real or caused by humans. So I thought I'd stick in 5 minutes. This is the record of the climate in the northern hemisphere and the southern hemisphere from about 1850 to the present day. The northern hemisphere has warmed up considerably. You notice the southern hemisphere is actually not quite a bit different than the northern hemisphere. In fact, it's essentially flat over the last 5 years. Now, what does this do to? Here's another set of graphs over a 1,000-year period of some major greenhouse gases: carbon dioxide, methane, nitrous oxide. And you might ask, what's happening over here? It's relatively flat, and all of a sudden it begins to slowly climb. And what's happened is the beginning of the Industrial Revolution, the beginning of burning of coal, and the beginning of actually a lot of prosperity in the world as we have access to this energy. So it's this rise of greenhouse gases from the Industrial Revolution that began to change things. Now, if you look at the measured temperature change in red, and you try to model the variation in the temperature of the Earth due to what we call natural variations, solar variations, and they do cycle. Large volcano activity emits a lot of sulfur dioxide in the upper atmosphere, which has a cooling effect on the Earth for several years. So a lot of volcanic activity actually cools the Earth down. Solar variations can make it go either way. And what you find in our climate models is you get this gray hash if you try to fold in all the natural variations. But if you fold in the increase in greenhouse gases due to humans, you get something closer to what we observe. This is not proof that humans cause climate change. It's suggestive that humans are connected with it. This and about a dozen other things like this then build a stronger, compelling case that the major part of what we see in the warming over the last hundreds of years is due to humans. Now, let's proceed and look a little bit more at the models. This is a scenario where we increase the amount of carbon dioxide in the atmosphere twice that of pre-industrial revolution. Pre-industrial revolution was 275 parts per million. Today it's about 380, but if you include all the methane and nitrous oxide that humans have put up, it's closer to perhaps 420, 430 parts per million carbon dioxide equivalent. So we're getting close to twice as much. And you see, and this is 4 times as much, and you see that it is very, very uneven. And this climate model, which was actually done about 8 years ago, shows that the northern hemisphere, especially on the polar ice caps, heats up considerably more. And in fact, there's a cooling in the southern hemisphere. And actually, in the subsequent decade, that has come to pass. Another bit of evidence that says we're not completely wet on our understanding of the climate. Okay, so here's some more predictions. I have to remind you of something the great American philosopher of the 20th century said. That philosopher was Yogi Berra. And he said that predictions are hard to make, especially about the future. So with that caveat, there are predictions as to what will happen in California. For example, I live in California. And depending on whether we have a very optimistic scenario or a very pessimistic business as usual scenario, the predictions are that the alpine and subalpine forests that make up the watershed of California will be either half gone or 90% gone by this century. And the snowpack will be anywhere from 30 to 90% gone by this century. So this is the watershed of California, and so even in the optimistic scenario, the technical term for this prediction, even the optimistic prediction, is we are in deep doo-doo. Here's an example of forest dying. This is a picture of British Columbia. This is dead standing pine in British Columbia. This is the live pine. And there was a prediction about a decade ago that perhaps 70–80% of the British pine will die by 2013. So it's, well, where are we in this? According to the British Columbia Ministry of Forest and Range in 2006, they're halfway there today. 40% of the standing British pine has now died. But how could this be with only a few degrees change? It's because the pine bark beetle was no longer killed in the frosts at winter. And then their population went crazy, and that ravaged the forest. It's a parasitic thing. It's a biological thing that caused such a great change. The pine forests in North America are beginning to die on schedule. There's a chance that fertile land would become desert. There's great swaths of desert, for example, the Sierras. And what you see in red and yellow are the boundaries between desert and fertile land. And in red and yellow, red, orange, and yellow are areas which would be threatened to become desertified. These desert boundaries can actually, if you're in Africa, you could see them traveling quite fast. It's a bit scary because the countries, especially around the equator, where some of the poorest people are, will be most threatened in the agriculture in southern India, in sub-Saharan Africa, in parts of Brazil. Also in the Midwest, this is a picture of 6 years of drought in the Midwest, and this used to be farmland. That was a temporary thing, but if we go into several degrees warmer, as suggested, this could be a permanent event. There's another biological concern that is not in the IPCC report because it was considered too speculative. If you go to the northern tundra in Russia and in Canada, you have a lot of vegetation. The vegetation finally dies, it falls on the ground, moss bogs. But usually, for example, in Brazilian rainforests, the microbes recycle this vegetation into carbon dioxide and methane. It enters the atmosphere, some more stuff grows, it captures the carbon dioxide out of the atmosphere, and just goes around in a circle. In the north, that doesn't happen because the microbes in the frozen permafrost are asleep. And so you actually accumulate carbon over long periods of time, millennia. Now, imagine what happens, and the analogy I like to use is you have a piece of meat, for example, or whatever, in a refrigerator, and this food in the refrigerator can last a week before it begins to spoil. You put it in the freezer, and it can last months. Now, my wife will make me throw it away in less than a month, but it can last months. It's a few degrees different. The transition is between below freezing and above freezing. Below freezing, the microbes are very, very sleepy, and they don't munch on the vegetation. Above freezing, they come to life. So one of the concerns is this tipping point when the Earth warms up again by just a couple degrees, and we don't know what temperature. Then you begin to release the carbon in the tundra. How much carbon is there in the tundra? Well, the estimates, quite frankly, vary. It can be a factor of 2 more than all the carbon in the atmosphere, or as low as 1/3. But once you begin to release the carbon, the rate of release would be comparable to all the carbon emissions humans are putting up today, which means once that process starts, it's out of our control. We can stop all our carbon emissions, and it will carry on. Okay, so that's another point you don't really want to go close to.